Good afternoon to all of you. First of all, I want to introduce myself. Myself Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering. And today my content is GTU question paper solution of the subject of vector calculus and linear algebra of the December 2013. So up to question number 5 we already see. So let's see question number 6. Here is question number 6b, first part. Find the geometric and algebraic multiplicity of each eigenvalue of A, where A is equal to 2, 0, 1, 2. Now you can see A is a lower triangular matrix. Now what is the meaning of lower triangular matrix? In a square matrix, if from the main diagonal elements above that main diagonal elements all the elements are 0, that type of matrix we are called lower triangular matrix. So here you can see this is a 2 cross 2 matrix. This is our main diagonal, and above that main diagonal element there is only one element, and that is 0, right? So this is a lower triangular matrix. In lower triangular matrix, if you want to find the eigenvalue of such type of matrix, just main diagonal elements are the eigenvalues, right? So this is a lower triangular matrix, hence its eigenvalues are 2, 2, correct? So and also we have to find the eigenvector corresponding to the eigenvalue lambda is equal to 2, right? Because we want to find the geometric and algebraic multiplicity of each eigenvalue of this matrix. So what is the meaning of geometric and algebraic multiplicity? If any eigenvalue, right, just try to understand first of all the definition of the geometric and algebraic multiplicity of the particular eigenvalue. So if any eigenvalue lambda, right, if that eigenvalue lambda occur n times, right, as an eigenvalue, so the algebraic multiplicity of that eigenvalue lambda, that is equal to n, okay? And if corresponding to that eigenvalue, if we get m number of eigenvector, right, if corresponding to that eigenvalue, if we will get m number of eigenvector, then we can say that the geometric multiplicity of that particular eigenvalue lambda is m, okay? So clearly the algebraic multiplicity is depending upon the how many eigenvalue occur as an eigenvalue, and the geometric multiplicity which is depending upon the how number of eigenvector corresponding to that eigenvalue. So that is the difference between geometric and algebraic multiplicity. So now you can see here we have only eigenvalue is 2, and 2 occur 2 times as an eigenvalue, correct? So clearly the algebraic multiplicity of eigenvalue 2 is equal to 2, okay? Now we want to find the geometric multiplicity of that eigenvalue 2. So for that definitely we have to find the eigenvector corresponding to that lambda is equal to 2. So here is a method to find the eigenvector. The eigenvector x corresponding to lambda is given by a minus lambda I into x, that is equal to 0. So a minus lambda I, that means in a matrix A we have to add minus lambda in the main diagonal. So here we get 2 minus lambda 0 1, 2 minus lambda x1 x2, and that is equal to 0 0, right? Now put lambda is equal to 2 in this matrix. Put lambda is equal to 2 in this matrix. So we get 0 0 1 0 into x1 x2, that is equal to 0 0. So 0 into x1 plus 0 into x2, that is equal to 0. So from that we don't get anything 1, but the second row, that is 1 0, so that means what, x1 1 into x1 plus 0 into x2, that is equal to 0. That means x1 is equal to 0, but x2 we cannot say anything about x2, so x2 is a free variable, right? So take x2 is equal to t, and what is our eigenvector corresponding to lambda is equal to 2, that is 0 1, correct? So x1 is 0, there is one free variable, we take x2 is equal to 1. So the eigenvector corresponding to lambda is equal to 2, which is 0 1. Now you can see only the one eigenvector we have corresponding to lambda is equal to 2. So the algebraic multiplicity of lambda is equal to 2 is 2 and the geometric multiplicity of lambda is equal to 2 is 1, correct? So here is the answer of this question. Here is a question that what is a geometric and find the geometric and algebraic multiplicity of each eigenvalue, but here we have only just one eigenvalue which is 2 and occurring 2 times, so that's why algebraic multiplicity of 2 is 2, and corresponding to that lambda is equal to 2 we have only one eigenvector, so that's why the geometric multiplicity of lambda is equal to 2 is 1. Okay, so here is a complete the solution of this question, and this question was asked in 2 marks in that question paper. Next question, question 6b, second part. U is equal to u1 u2 and v is equal to v1 v2 be vectors in R2. Verify that weighted Euclidean inner product uv, that is equal to 3 u1 v1 plus 5 u2 v2 satisfied the 4 inner product axioms. This question was also in 2 marks in that question paper. We know that what inner product space, what is the definition of inner product space? Definitely we have to satisfy the 4 conditions. What 4 conditions? What are the 4 conditions? The first one is commutative law, that means for any uv belongs to the vector space V, right? Here our vector space is R2, so for any uv belongs to R2, inner product uv is equal to inner product vu, using that inner product which we define in the statement of this example, right? We have to use this weighted Euclidean inner product, that inner product u is equal to 3 u1 v1 plus 5 u2 v2. So that using that Euclidean inner using that weighted Euclidean inner product, we have to prove all the 4 conditions for the inner product space. So first one is commutative law, that is inner product u is equal to inner product vu. Second one is associative law, that is inner product uvw, that is equal to not called the associative but inner product uvw, u plus vw, that is equal to inner product uw plus inner product vw, right? Third one is inner product ku v, that is equal to k inner product uv, and the fourth one is if inner product u with u itself always greater or equal to 0. If that is equal to 0, if inner product u with u is equal to 0, that means u is equal to 0, where 0 is 0 means 0 vector, right? Whatever our vector space, that is 0 element of the vector space. So let's try to prove all the 4 conditions, all the 4 axioms which we have to prove here. So first one is commutative law. We also need another 3 vector u, v and w, so that's why already u and v are already given in the statement that u is equal to u1 u2 and v is equal to v1 v2. So let's take another vector, third vector, let w is equal to w1 w2, which we already which we need in to prove this 4 conditions. So let w is equal to w1 w2 and alpha is any scalar, so alpha belongs to R. So first one is commutative law, inner product uv, that is equal to 3 u1 v1 plus 5 u2 v2, but that can be definitely written as 3 v1 u1 plus 5 v2 u2. Okay, what is inner product uv? That is 3 u1 v1 plus 5 u2 v2, but that can be definitely expressed as 3 v1 u1 plus 5 v2 u2, and that is equal to inner product vu. Okay, so this is commutative law. Next one is this one, that inner product u plus vw, that we have to prove that inner product uw plus inner product vw. So that is equal to 3 into u1 plus v1 w1 plus 5 into u2 plus v2 w2. So that is equal to 3 u1 w1, just simplify this bracket, so we get 3 u1 w1 plus 3 v1 w1 plus 5 u2 w2 plus 5 v2 w2, that is equal to 3 u1 w1. This 2 term we put together, 3 u1 w1 plus 5 u2 w2, right? So first we write this 2 terms, 3 u1 w1 plus 5 u2 w2 and plus 3 v1 w1 plus 5 v2 w2. So that is equal to inner product uw plus inner product vw. okay, because the first two terms is exactly the inner product uw you can write, and the another two terms that can be expressed as exactly inner product vw. Okay, so this is the second property. Third one, alpha uv that is equal to inner product alpha u with v, that is equal to by definition 3 into alpha u1 v1 plus 5 into alpha u2 v2. So that is equal to alpha into 3 u1 v1 plus 5 u2 v2. Okay, and that is equal to alpha inner product uv. Clear? So and the last property is inner product u with u, that is equal to always greater equal to 0, that we have to prove, and that is equal to inner product that is equal to 3 u1 square plus 5 u2 square, and that is always greater equal to 0. Clear? Now inner product u with u, that is always equal inner product u with u, that is equal to 3 u1 square plus 5 u2 square, that is always greater equal to 0, right? Clearly, but when we take inner product u with u is equal to 0, that means what? 3 u1 square plus 5 u2 square, that is equal to 0, right? And that means u1 is equal to 0 and u2 is equal to 0, both the coordinates are 0. That means u is equal to 0 vector in R2, that is 0 0. It is a coordinate wise, that can be written as 0 0, right? So thus all the four exams are satisfied by the given weighted inner product. So this statement is proof that we have to verify that basically that weighted equivalent inner product with this notation inner product u is equal to 3 u1 v1 plus 5 u2 v2 satisfied four of them, 4 inner product exams, and we already prove it, right? So this question was complete now, and this question was asked in 2 marks in this question paper, question 6b second part. Next question 6c. Given the quadratic equations x square minus 16y square plus 8x plus 128y, right, that is equal to 256. A translation will put the conic in the standard position. Name of the conic and give its equation in the translated coordinate system. This question was asked in 3 marks. The matrix form of the given equations, that is x transpose ax plus kx minus 256, that is equal to 0. Call it the first equation, where a is equal to 1 0 0 minus 16 and k is equal to 8 128. Okay, so this is a x square minus 16y square. From that one we get 1 minus 16 and this is 0 0, and k is equal to the coefficient of x and y, that is 8 and 128. And the matrix form of this equation is x transpose ax plus kx minus 256, that is equal to 0. Okay, now the eigenvalues of a are 1 and minus 16. Clearly this is a triangular matrix, upper triangular and lower triangular both, right? So basically this is a diagonal matrix, and the main diagonal elements are exactly the eigenvalues of the given matrix. So 1 and minus 16 are the eigenvalues of this matrix. Let x1 is equal to x1 x2 be an eigenvector corresponding to lambda is equal to 1, right? So let x1 and x2 be an eigenvector corresponding to lambda is equal to 1. So what is our to find the eigenvector, which matrix we have to use? We use that 1 minus lambda 0 0 minus 16 minus lambda, right? Correct. And in that matrix we have to put lambda is equal to 1. So basically we get 1 minus lambda. In 1 minus lambda, if you put lambda is equal to 0, so we get 0. Already here also 0 0, and this is minus 16 minus lambda. In that lambda, when we put 1, we get minus 17. So here is a matrix 1 minus 1 0 0 minus 16 minus 16 minus 1. So 0 0 0 minus 17 x1 x2, that is equal to 0 0. Now from that matrix we get 0 into x1 plus 0 into x2, that is equal to 0. So minus 0 is equal to 0 from that equation, but the second row, consider the second row 0 into x1 minus 17 into x2, that is equal to 0. So minus 17 x2, that is equal to 0. So x2 is equal to 0, and we take x1 is equal to 1. Okay, we take x1 is equal to 1 because x1 is now free variable. So if we take x1 is equal to k, so our eigenvector corresponding to lambda is equal to 1 is 1 0, and similarly also we can find the eigenvector corresponding to minus 16. How we find? Let's see. This is 1 minus lambda 0 0 minus 16 minus lambda. So put lambda instead of lambda, if we put minus 16, right? So we get 1 0 0 minus 16. You can see, try to understand from that one. So this is our matrix 1 0. This is our matrix 1 0 0 minus 16, right? Already we find the eigenvector for lambda is equal to 1, that is 1 0, right? Okay, so this is our eigenvector corresponding to lambda is equal to 1. Now if you want to find the eigenvector corresponding to lambda is equal to minus 16, definitely we have to use this matrix 1 minus lambda 0 0 minus 16 minus lambda. In this matrix we have to put lambda is equal to minus 16. So what we have to get? 1 minus minus 16, so 17 0 0, and if we put lambda is equal to minus 16 here, we get 0, right? This is already a in row echelon form matrix, and from that matrix we get 17 x1, that is equal to 0, right? Because here we already x1 and x2, that is equal to 0 0.